So let's start this chapter, chapter 1, introduction and basic concepts. So So the objectives of this chapter is to identify actually the unique vocabulary associated with the thermodynamic, like actually those vocabularies and some general definition, like the definition of the word thermodynamic itself, also the definition of the different kind of system, open and closed system, state postulate, the equilibrium state of a system, the difference between process and cycle. All of this definition will be actually defined through the introduction course. Also, we'll review the system of unit, the standard system of unit, and also the English system of unit. We'll be following in this course, inshallah, the standard system of unit, but you have to know about also the English system of unit. We need also to review the concept of temperature and temperature scale, including Celsius, Fahrenheit, Kelvin scale. All of this scale will be discussed, and how we can relate them to each other, and how we can measure the temperature itself is a concept of operation. Also defines the pressure and different pressure, including gauge pressure and also that the absolute pressure and the difference between them. And we'll consider also the pressure measuring devices, how we can measure the pressure using which devices. By the end of this chapter, we'll be considering a kind of introduction or systematic approach how to solve any engineering problem. Type thermodynamics and energy. Thermodynamics actually is thermodynamics is the science that actually that deals with energy and the matter and the laws governing their interaction. Laws governing the interaction between mass and the energy are the first and the second law of thermodynamics. So thermodynamics is mainly the first and the second law of thermodynamics. Energy is defined as the ability to make changes. If you have the energy, then you can move actually from one location to another. You can study hard. If you have energy, you can do more and more. So energy is the ability to make changes. The word thermodynamic itself, we can get it back to it again. It's coming from Greek word therm, which means heat, and dynamics, which means power. So this science, thermodynamics, is the science of conversion between heat and power, or heat and work. Okay. Type how we can control actually the transfer of energy. Energy actually is controlled by what's called actually the conservation of energy principle, or what's called actually the law of mass action. You know, actually this law which states actually energy cannot be created or destroyed. Energy can just be converted from one form to another form. Okay, so let's look at actually this example here. We have actually in this example we have a stone that is actually suspended at the top of mountain. So that means let's consider this. Okay. Just minimize little. You should be able to see it now. Okay. So if we have here a stone like at the top of a mountain or something, so it have a kind, this is actually suspended at the top of this, suspended at the top of the mountain, then this means its kinetic energy is equal to 0. So the kinetic energy is equal to half m multiplied by v squared. And its potential energy, as actually it is suspended at a given elevation. So if you have a body that is actually suspended at a given elevation z, This means actually the potential energy will equal to mg multiplied by z. Okay, so if at the top of the mountain, if we have potential energy equal to 10 units and actually kinetic energy equal to 0, so the total energy is equal to 10 units. So if you let actually this stone to fall down, sorry. So in this case, this stone will accept the kinetic energy. So kinetic energy will be increasing in this case, but it will be losing height, so it is losing actually potential energy. But the total energy should be remaining the same, as actually energy cannot be created. Energy cannot be created or or destroyed. So at a given height here, at a given height here, if you see, if we have potential energy equal to 7 units, so the kinetic energy should equal to 3 units, then the total energy should equal to 10 units. First law of thermodynamics actually. First law of thermodynamics is the same as actually the conservation of energy principle. Which actually, but in this case, it is applied to a thermodynamic system. So if you have any thermodynamic system, so if you do have actually any system, we have energy input, En, total energy input to the system, and we have actually part of energy is leaving this system, energy out. So we have energy in, and we have energy out, and we have part of this energy, delta E, is stored actually within this system. So the first law of thermodynamics, so the first law of thermodynamics, the first law of thermodynamics in this case will say as energy cannot be created or destroyed, so the energy input to the system should equal to the energy output plus the part of energy stored within the system, delta E within the system. So we can say energy in will equal to energy out plus the change of energy within this system. Or the first law of thermodynamics, we can just say the difference between energy in minus energy out will equal to the change of energy within this system, delta E within this system. And this is actually the first law of thermodynamics. So it is just a conservation of energy, that energy cannot be created or destroyed. So energy input to a system will equal to energy out plus the change of energy, delta E within this system. Okay. This is the first law of thermodynamics. Here is an example. As you can see, this actually, this guy, this samurai guy here, you can see we have energy input equal to 5 units, and we have part of energy. He consumes actually a kind of 4 units of energy leaving his body in terms of activities or something. Then actually he's storing 1 unit of energy within his body in the form of fat, because actually energy cannot be created or destroyed. So as we have 5 in, we have only 4 out. That means actually we have 1 unit is remaining within his body. And the first law of thermodynamics in general, we can say it is dealing with the quantity of energy, not the quality of energy. Second law of thermodynamics is dealing with the quality of energy. How is this? Second law of thermodynamics states actually any process has a direction. This process has to proceed from the high energy potential to the low energy potential. Like actually this hot cup of coffee, if you see here, we have this hot cup of coffee existing at 70 degrees C in a surrounding room at 20 degrees C. So the direction of heat transfer will be from the hot cup of coffee to the surrounding low temperature. If you reverse the process, so the process actually cannot go, and the second law of thermodynamics will state this process is invalid process. But if you apply the first law of thermodynamics for this invalid process, it will be satisfied because it is just energy balance, just will have a negative sign in this case. Okay, and this is the difference between first and second law of thermodynamics. We'll be talking inshallah in details about the first and second law of thermodynamics and their mathematical proofs. We'll be talking later on chapter 4, from chapter 5, chapter 6, and also in chapter 7. As actually this is the main subject of this course. But to study any thermodynamic system, we have 2 approaches. We have the first approach is called the classical thermodynamic, which is the microscopic approach, or the general engineering approach, which is actually the main approach in our engineering life. Classical thermodynamic, as actually in our engineering life, we are concerned about the average behavior of the system. So actually this system is the general applied system in the engineering life. Like if I need to measure the temperature of this coffee inside this hot cup of coffee, then in this case I will just insert a kind of a thermocouple inside this cup and I will measure the average temperature. Okay. This is considering the classical thermodynamic or the macroscopic approach, which is actually the average behavior approach. Moving to the classical, the statistical thermodynamic or the microscopic approach, this means actually in this case, in order to measure this temperature, I have actually to measure the temperature at each molecule, and then I have to integrate through the whole system. Then I can calculate actually the temperature. Then I can calculate the temperature for the whole system. So actually it is a tedious approach, but it is actually very accurate approach. But actually in our engineering life, as we said, we are concerned with the average behavior of the system. So usually the classical thermodynamic approach is applied. But in some application like the nuclear reactor or something, we are dealing at the nuclear level. So in this case, we need to apply the statistical thermodynamic because in the nuclear reactor, we have each atom is being heated by a neutron, and then this neutron will result actually in division reaction, and it will result in some energy, and then the reaction will result in 2 additional neutrons, and each neutron will go to actually to the next atom, and it's a kind of a chain reaction. Okay. Then in this case, to study this system, we have to consider the statistical thermodynamic approach. But otherwise, actually, in all other engineering applications, we can follow the classical thermodynamic approach. Here, actually, for the application here, you cannot find actually in our life actually any system that does not belong actually to thermodynamics. So you should have any system should have a kind of mass transfer or energy transfer, and whenever we have mass transfer or energy transfer, then we can apply the thermodynamic in terms actually of the first and second law of thermodynamics. Here are some examples like this house. If you have solar collectors, then we can take the heat from the sun. We can take this heat actually to heat up water. Then you can have actually a hot shower here using this hot water, or you can use it actually in different applications. And in this case, we have heat transfer to the water and we have flows going. So we have energy transfer, mass transfer. Then we can apply the first law of thermodynamics. We can calculate the amount of heat transfer, and also can calculate the mass flow rate, and we can calculate also the efficiency of this heat transfer process. Also, we have in this boat or something, we have a diesel engine. We burn the fuel, then we can generate heat under high pressure and high temperature. This heat we can force actually the piston of the internal combustion engine. It is similar to the engine in your car, but most of the car are petrol or gasoline engine, but it is the same idea. We burn the fuel to push the cylinder, then we can have a kind of movement like this. Actually, same system is applied in the boat. We have actually shaft bar is generated using the internal combustion engine, which is a diesel engine. Then we can actually drive a propeller to move this boat. Like the aircraft, also we burn the fuel to have a thrust to move, thrust force to move this actually heat engine. And in power plant, electrical steam power plant, we burn the fuel to boil water to convert it to steam. Then we can expand this steam inside the turbine. Then we can generate shaft power, which can be connected to an electric generator. Then we can generate electrical power. Thermodynamic has two main applications. When we convert heat into work, like all of this system, we convert heat into shaft work. Then in this case, actually, it is called a heat engine. But there is another application which is called the refrigeration system. In the refrigeration system, we do the opposite. We convert, in this case, the work. We convert it into a form of control of heat. So in this case, like the fridge at your home, we consume electrical power. Then we can convert this electrical power into mechanical shaft power through an electric motor. And this shaft power is used actually to drive a compressor to run the Freon through actually inside the fridge, so that actually we can cool down the food in the food compartment. And in this case, the mechanism is to convert electrical power, which is a kind of work, electrical work power. We can convert it into the form of heat so that we can absorb the heat from the food compartment. So this is the system of the refrigeration system, and it is rare actually to find any system in our life that does not actually belong to thermodynamic, and in this case we can apply the first and the second law of thermodynamics. We'll get back again to the board so that actually we can I will just give you a kind of introduction about the dimensions and units. Okay. Okay. Hopefully, inshallah, we'll resume physical classes again. I'm just trying to put you as much as I can in the physical, in the real physical situation. But I'll do my best. Inshallah, hopefully we can return very soon. So for dimensions and unit, for the dimensions, I think you know about this. We do have three basic dimension. We have mass, its dimension is m. We have length, its dimension is l. And we have the third basic dimension, which is time, and its dimension is st, small t. And from those actually three basic dimensions, we can generate the dimension of any quantity, like the velocity v. Velocity is the length divided by time, so its dimension is just L over L capital over T. And this is the dimension of the velocity. For the acceleration, acceleration is velocity over time, so its dimension will be L divided by divided by T squared. Like this, we can generate the dimension for the force. Force actually is mass by acceleration. Mass, its dimension is m, acceleration is L divided by T squared. Like this also we can define for the case of work. Work is defined actually as a force applied to move actually a body a certain distance L, so it is force multiplied by distance L. Force, which is actually mL divided by T squared, and we have to multiply by L, so it will be mL squared divided by T squared, and this is the dimension actually of the work. Like this also we can define the dimension of the term, which is the power. The power is actually the force multiplied by velocity, or it is actually the rate of work done. It is the work divided by time. Work, which is force multiplied by distance, divided by time, so it will be L over T. L over T is V. So in this case, the power is equal to force multiplied by velocity. So it is work divided by time. So the dimension of the work is m L squared divided by T squared divided by time. We have to divide by time, so it will be mL squared divided by T cubed. Also, we have another term, which is the pressure. Pressure is the force applied, the normal force applied per unit area. So its dimension, the dimension of this unit, the force is mL divided by T squared, mL divided by T squared, divided by area. Area is length squared, so it will be L squared. So the square will go with L, so it will be m divided by T squared by T squared by n. And this is actually the pressure. So based on this, actually, we have three basic dimensions, and based on those three basic dimensions, we can generate the dimension of any quantity, like what we can see. Like, what about the unit? Actually, each quantity has its own unit. Like here, the velocity, it is distance over time, so the unit in SI, in the standard system of unit, is meter per second. For the acceleration, it is velocity over time, so it is meter per second square. For force, it is mass by acceleration, so it is kilogram. Acceleration is meter per second square, kilogram meter per second square, which is called as Newton. Type work is force by distance. Force is Newton by distance, so this is actually the unit is actually Newton multiplied by meter, which is equivalent to what we call joule. So 1 joule is equal to 1 Newton per meter. Okay. Now, what about the power? Power is work, rate of work done, work over time. So it is joule per second. Joule per second is equivalent to watt. Okay. And I think you know about this. The pressure is force over area. So the standard unit force is Newton by area is meter square, and you know Newton over meter square. This is what we call actually Pascal. So Pascal is Newton per meter square, and this is the unit used to measure the pressure in this case. Okay. But in addition, actually, to this unit of pressure, we have another unit which is bar. 1 bar, which is almost equal to 1 atmospheric pressure. It's our atmospheric pressure, 1 atmosphere ATM. 1 bar is equal to 10 to the power 5 Pascal. And those are actually the standard system of unit. We have also, in addition to this, some additional ideas here. If you look here, on this table, you can see here if we have a small amount of, let's say, small pressure value, then in this case, instead of using Pascal, we can use actually the name DC. DC Pascal, this means 10 to the power minus 1. We have also Santi, which is 10 to the power minus 2. We have also milli, 10 to the power minus 3, micro, 10 to the power minus 6, and I think you know about this. If we have bigger amount, then we can use kilo, which is 10 to the power 3. Kilo Pascal is equal to 10 to the power 3 Pascal. We have mega, 10 to the power 6. We have giga, we have tera, and we have actually all of this multiplication unit. So in this case, actually, if you have bigger amount, you can use kilo, mega, giga, tera, all of this. If you have a small amount, you can use actually DC, santi, milli, and all of this unit. But all of these actually are applied in what we call the standard system of unit. We have another system of unit which is called the English system of unit. As you can see here from this system is it does not have real physical relation between all of the system. Just they are actually ancient devices that has been used, and they are still applied actually in. They are still applied in United States and also United Kingdom. But you have to know about, because if you are working outside and you have imported a kind of tubes or pressure gauge or any device, you will find actually the units are defined actually in the English system of unit. If this device is coming from United States or mainly also United Kingdom. So the mass in the English system of unit is calculated in pound mass, which is equal to 0.45 kilogram, about half kilogram. But in your exam, it's not about, you have to write down this, and if it came to your exam, we will give you this conversion factor. You don't need actually to remember those numbers. 1 feet is equal to a kind of 0.3 meter, and force is mass by acceleration. Force in the English system of unit is calculated in pound force. 1 pound force is equal to 32.174 pound mass feet per second square. But how we can convert from pound force in the English system to Newton? So in this case, this is the definition of pound force. We can just convert pound mass by kilogram by multiplying by this number. Convert feet by meter by multiplying by this number. Then multiply the three numbers, this number by this number and by this number, and this will be the relation between pound feet and pound force and Newton. Work is force by distance. Work is calculated in joule, which is Newton meter, but there is another unit which is very common one, which is the calorie. 1 calorie is equal to 4.18 joule, and we have another unit, BTU, which is British thermal unit, is equal to a kind of 1.05 kilojoule. Okay. There is also another property, which is the weight. It's actually the most common example is the weight actually of the body, of our body or something. So the weight. So weight is mass multiplied by gravitational acceleration. So weight, it has a symbol W. And it equal to mass multiplied by G, which is gravitational acceleration. Gravitational acceleration have a value 9.81, which you should keep in mind. So W is the weight, which is equal to mass multiplied by gravitational acceleration. The gravitational acceleration is 9.81 meter per second square. You have to keep in mind. Okay. But we have another property, which is gamma, which is called actually the specific weight. The specific weight is the weight per unit volume. Just be careful, in this course, we will consider any specific property, like a specific volume, specific internal energy, specific enthalpy, anything. Any specific property in this course is the property per unit mass. Only we have a special case, which is a specific weight, gamma. A specific weight is the weight per unit volume. Okay? But any other specific property is the property per unit mass, not per unit volume. Only specific weight is per unit volume. Type weight is equal to mg, mass, multiplied by gravitational acceleration divided by volume. Type by definition, we have actually the density of rho is equal to mass divided by volume, which is kilogram, calculated in kilogram per meter cube. Okay, then we can say mass equal to density multiplied by the volume, and substitute here. So the specific weight equal to density by volume multiplied by gravitational acceleration divided by volume. So V will go with V, so it will equal to rho multiplied by gravitational acceleration. Its unit is weight, which is force per volume, Newton per meter cube. So specific weight is equal to rho G. Type the final thing to tell to end up actually with this with today's class. Something is called actually the dimensional homogeneity. Dimensional homogeneity in just a very brief way. If you have an equation A plus B equal to C plus D, so that means the unit of term A should be the same as unit of term B, same as C, same as D. So if the unit of term A, let's say Newton, so this term should be Newton, this term should be Newton also, which is the unit of the force, and all terms should have the same unit. If it is pressure Pascal, then this should be Pascal. It can be bar, pressure in bar, then actually all terms should be in bar. And this is what we call actually the dimensional homogeneity. Okay, I will inshallah stop here. I will stop here for today, and inshallah I will continue by the next class inshallah. Yalla, assalamu alaikum.